Hey there, this is Mr. H. I'm making these videos to help any physics students out that are trying to prepare for the AP Physics 1 exam in the year 2020, which is a uniquely different year. So I put together a few mock exams, what I think would be a good replication of what you might expect as far as content and difficulty level. So I hope these help anybody who needs them. Before we get started on the mock, I've attached a few reference sheets that include equations, strategy steps, and tips on paragraphs, short answers, and graphs. If you want to take a few moments and screenshot these next few slides. Okay, let's get started. Probably the best thing to do is to treat this like it really is the exam, and pause the video, try to do the problems yourself, and then press play afterwards to see how it worked out. Okay, for the first question, we have a car that's driving at speed v around a circular path of radius r on a flat road. Inside the car, there is a mass suspended from a spring that is tilted at angle theta. We're then asked to draw a free body diagram labeling all forces acting on the mass. Well, I have 3 hints for free body diagrams. The first thing we want to do is to consider invisible forces such as gravity. We're on Earth, so we're going to have weight vertically downwards. I drew it with 3 units. They're probably going to give you some sort of representation on a grid here, so let's do 3 units downwards. We don't have an exact amount for this particular one. They gave us m. The next hint is to consider contact forces. So we're going to look at that mass and look for a contact point. It's in contact with the spring, and the spring is pulling it. So we need to draw a force vector for the spring pulling the mass. Now, the last hint is to consider acceleration. This is going about a curve of radius r on a horizontal flat road. That means the acceleration needs to be towards the center, so it's going to be to the left from this vantage point. Now, on our free body diagram, we need to make sure that it looks like the net force is to the left. And since there's no vertical acceleration, any vertical components of force need to cancel out. We drew the weight with 3 units downward, so we need to have the vertical component of the spring force to be 3 units upward so that they cancel. Question B. Derive an expression for the spring constant K in terms of the other fundamental constants listed, including little g. So this is clearly a problem-solving prompt, and we have problem-solving strategy steps for things like this. This is a force question, so we'll be using the force strategy steps previously listed earlier in the video. Step 1 is to identify what they're asking for. That should be done when we have a symbol and a question mark. They asked for spring constant K, so we write K equals question mark. Steps 2 and 3 have already been completed because the picture was already drawn for us, and the previous prompt we did a free body diagram. So we're on step 4 right now. Step 4, you analyze your free body diagram to create equations. One equation you can always create is a net force equation. Since we're going in circular motion, we do net force as net centripetal force, inwards forces minus outwards forces. According to the diagram, inwards is to the left, so we need a force component to the left for F spring. Now, we already defined theta as from vertical, so opposite to that would be sine theta. So force spring sine theta is your net centripetal force. There are no other force components towards or away from center. Step 5 is to apply laws and formulas that are related. In this case, we're dealing with circular motion, so Newton's second law for circular motion, Fc equals m times centripetal acceleration, is going to be applicable here. And we had a spring force, so the spring force equation is also applicable. Now we have a system of 3 equations and 1 unknown k, So we're going to use algebra to solve for k. So let's get to k by itself, and you get this expression. The next question is a little bit unique and different. It says, while it was driving around the curve, the spring system was oscillating with period t1, and sometime later, while it was parked, the spring system hung vertically and was set into motion again, and period t2 is observed. And then you want to compare t1 to t2 and explain your reasoning. I want to take a moment and remind you of the strategy step for these short answer problems. They're going to ask you to pick one of these check marks, and you want to think about why you're choosing the appropriate relation between the two periods. So what kind of principle would guide you for determining these relations for spring periods? And hopefully we're thinking of the spring period equation, and then this is going to be the thing that supports our answer and justifies the thing that we choose. So what was different when we stopped the car and these hung vertically? Well, the equilibrium position might be different, but the mass and the spring constant are not different. So if period is determined by mass and spring constant, who cares where the equilibrium position is? So we should be checking the box for T1 equals T2. So now all we have to do is put that into words. So the period of the spring system is unaffected by a change of equilibrium position. The spring system only depends on factors of mass and spring constant, which are the same in this case, so the period is the same in this case. Alright, it's time for the next page. Take a moment, look at the questions on this page, try your best, pause the video, and when you've completed your best attempt, press play, resume the video, see how you did. Okay, the first question says that two spheres of identical radius but unknown mass approach each other on a frictionless two-dimensional flat plane. They collide, and their x-coordinates are plotted in this graph. The first question asks, was momentum conserved in the x direction for the events described previously? Now let's examine the information they gave us. They described the collision as happening on a two-dimensional flat surface with no friction, and they also gave us the information of the x-coordinates during the event. Now if you're looking at the graph, my advice for looking at graphs is to ask yourself, does slope mean anything, and does area mean anything? This is a position versus time graph. So rise over run, the slope would be velocity. So we have information of velocities here. I also suggest look at the product x times t. We don't have any meaningful physics principle for x times t. So what we can get from the graph are the speeds or velocities before and after the collision of both masses. However, we don't know what masses they were because it says unknown mass. So we can't tell the momentums from this picture. We can only tell the velocities. Well, what do we know? We know that this event happened on a frictionless flat plane. And we also know that because of Newton's second and third laws, when these two objects in this system of two objects collide and push off of each other, they change each other by the exact same amount in terms of momentum. So the total momentum of this system has to stay the same. We're going to check the box for momentum is conserved, and our reason has to do not with the graph, but with the law of conservation of momentum. All that remains now is to put that into words. So you want to say something along the lines of momentum is conserved in the x direction, or all dimensions, as justified by the law of conservation of momentum for a system with no net external forces. the next prompt asks us to consider that the collision was head-on, and what would that say about the elasticity of the collision? Now, elasticity tells you how much of the mechanical energy is restored due to the event. Now, if you looked at the speeds, remember the graph gave us that information of speed or velocity before and after. If you look at the final velocities, you could see that the system lost relative motion. So that means we've lost some kinetic energy, at least in the x direction. What does that say about the y direction? Well, they also told us that it was exactly head-on. So because it's exactly head-on, we don't have to worry about the second dimension. It was all a one-dimensional event. So now all we have to do is put that into words. So we want to say something along the lines of the collision event is partially elastic. It maintains some, but not all, of the relative velocity between the two masses, which indicates that kinetic energy is reduced, but not reduced to the level of having zero relative motion. Now we consider the exact same spheres, but they're approaching each other kind of off-center. So they're going to collide, not head-on, and we're going to compare the magnitudes of their final angular velocity after the collision. So hopefully when you're evaluating a collision like this, your mind goes to those key overarching laws, such as the law of conservation of angular momentum in this case. We could treat this like a problem-solving question that asks for angular momentum final, and we do the problem-solving steps. We get an expression that says the moment of inertia of the blue ball times the final angular velocity of the blue ball equals moment of inertia of the red ball times final angular velocity of the red ball. But how does that tell you which one is greater? We would have to know what their values for I are. What information have they given us about I? They tell us that early on these are the same exact geometries. They're both solid spheres. But then they gave us, if you recall, they gave us this graph. This graph gave us some information about how much inertia each of those solid spheres had. If you look carefully, you can tell that the red sphere changes its velocity greater than the blue sphere does, which means that the inertial mass of the blue sphere has to be greater than the inertial mass of the red sphere. How does that help us with moment of inertia? Well, let's go back to comparing these products here. If the blue ball has a greater moment of inertia, then it wouldn't need as great of a final angular velocity such that their angular momentums would be the same. Therefore, red has to have a greater change of angular velocity. So now we want to put this in paragraph form. This is the paragraph length response, so we want to do a thorough job. We want to present our argument in logical sequence. We want to use applicable and relevant physical laws. We don't want to add any extra information, and we want to support our selection. So something like this might be a good paragraph. This has been Mr. H Physics. Thank you for watching. I hope this has been helpful. Good luck out there.